Okay, we're going to be talking about identity matrix and inverse matrix. In our book, it's section 4.4. Let's start with the definition of identity matrix. An identity matrix is a square matrix with ones on the principal diagonal and zeros in all other positions. Okay, so I've got three examples here. A one-by-one identity matrix, it really doesn't have all the color and characteristics of an identity matrix because there's only one element, but this is what it would be. With the 2-by-2 identity matrix, you can clearly see what we call the principal diagonal, and that's from the upper left to the lower right. And so for it to be an identity matrix, then these numbers have to be ones and all other entries have to be zeros. And of course, these are the only other two, and they are zeros. See a little better picture in a 3 by 3 identity matrix. Again, upper left to lower right. This is considered the principal diagonal, and all of these are ones, and then all the other entries in this matrix are zeros. These are identity matrix. Now, I want to remind you of what the identity is in real numbers. The identity, the multiplicative identity, I should say, because we're going to be multiplying these matrix down here. So these are multiplicative identities, but in real numbers, the multiplicative identity is 1 because 1 times anything is itself. So it yields, the answer is the problem, one of the factors in the problem, the factor that's not the 1. Okay, well, that's going to be true in matrix as well. So in matrix, the identity matrix is the matrix that you can multiply by, and whatever matrix you're multiplying it by, it keeps its identity. It doesn't change. Okay, let's move on. All right, now just a little review from the last section. We need to remember that for matrix multiplication to be defined, or let's say possible, then the number of columns of the first, or we could say the one on the left, must match rather the number of rows of the second, or the one on the right. And the product has the dimensions rows of the first and columns of the second. Okay, so just a little review there. All right, so here we're talking about identity matrix again, and just kind of showing you in general that I times A, if I was the identity matrix for whatever size matrix A is, I times A is A. And as we know from previous lessons, that matrix multiplication is not commutative. So if we put the identity matrix second, it may or may not be the same size matrix, and A times I is equal to A. So there could be a left identity matrix for any given matrix A, and there could be a different right identity matrix for any given matrix A. All right, let's just take a look at one. So if we take this matrix 1, 2, 3, 4, 5, 6, not very creative, and we look at what the dimensions are. It's the number of horizontal groupings, or the number of rows, which is 2, and by the number of columns, or the vertical groupings, and I see 3. This is a 2 by 3 matrix. Okay, so down here I've illustrated what the left side identity matrix would be for this matrix A. Now, if you think about it, matrix multiplication, these numbers here have got to be the same. So if I'm going to put the identity on the left side of it, then whatever the rows is going to have to be what the columns are here, and of course we know identity matrix are square, so if that's a 2, then this has got to be a 2. So the left-hand identity matrix for A is a 2 by 2 identity matrix, one on the principal diagonals, other entries are 0. But if we decide to put it on the right of this equation, or excuse me, this matrix, then these two numbers would have to be the same, so they would have to be 2 3s right here, and of course we know that the identity matrix is a square matrix, so if one of them's 3, the other one's got to be 3. And then this would be the right-hand side identity matrix for this particular one that's a 2 by 3. Now, of course, that would change with different pairings of rows and columns, but we're dealing with a 2 by 3, so we wanted to show you the left-hand side would be a 2 by 2, and the right-hand side would be a 3 by 3, making the dimensions work out for multiplication. Okay, moving on. Okay, example 1. Let's just illustrate that the identity matrix actually does what we say it, or what it's supposed to do. Okay, so we're taking that 1, 2, 3, 4, and we're going to go ahead and multiply it by this 2-2 identity matrix. Now, with all multiplication problems with matrix, you always take the one on the left and break it up into rows, and the one on the right we cut up into columns. Okay, this is a review. Then we go over here to our answer, and to find out what goes in this position of the answer, of course, I skipped over noting that these are the same, and we take them out, and then what's left, 2 by 3, is what the answer has to be, and I've gone ahead and made a 2 by 3 answer blank. You always want to make an answer blank so you can look at the positions to find out what you multiply to get what goes here. So this is, and I won't write all these out, but I'll go ahead and do this one. This is row 1, column 1. So in our problem, we'll label our rows, and that's those are always the one on the left is broken up into rows, and I'll label my columns. And I'm not going to do this with every problem, but we'll do it on the first one. Okay, so this is row 1, column 1 of our answer. In our problem, what we've designated as row 1, those numbers will multiply by the numbers in column 1. And again, reviewing matrix multiplication, we take the first in the row times the first in the column, and that's going to be 1 times 1, or 1, and then take the second in the row times the second in the column. So we have 1 plus 0, which is 1. Okay, let me take those lines out of there. That gives us 1 right here. Okay, this is row 1, column 2 of my answer. So I'll take the numbers in row 1 and times them by the numbers in column 2. I'm going to pair first with first. So 1 times 2 is 2. 0 times 5 is 0. 2 and 0 is 2. 2 goes here. Okay, this is row 1, column 3 of my answer. So I take the numbers in row 1 and I times them by the numbers in column 3. Taking the first in the row, timesing it by the first in the column. We'll do that in our head. 1 times 3 is 3, plus 0 times 6 is going to be 0. 3 plus 0 is 3. So we put a 3 here. Okay, now this is row 2, column 1 of our answer. So we take the numbers in row 2 and times them by the numbers in column 1. First in the row times first in the column. 0 times 1 is 0. Plus, and it's always plus between them, 1 times 4 is 4. 0 plus 4 is 4. 4 goes here. And this is row 2, column 2. We take the numbers in row 2 and times them by the numbers in column 2. We pair up first in the row times first in the column, or 0 times 2 is 0, plus second in the row times second in the column. 1 times 5 is 5. 0 plus 5 is 5. And then here it's row 2, column 3 of our answer. We take the number in row 2 and times it by the number in column 3. First in the row times first in the column, or 0 times 3 is 0. Second in the row times second in the column, or 1 times 6 is 6. 0 plus 6 is 6. And we put the 6 here. So here's our answer, 1, 2, 3, 4, 5, 6. It matches this, and clearly then the matrix identity is doing what it's supposed to do. You take any matrix, multiply it by the identity, and the matrix doesn't change. It keeps its identity, if you please. Okay? We'll try one more down here, and then I'll give you a couple to do. Okay, so on this matrix 3, 5, 4, 1, 0, 2, then we're going to, since it is a 2 by 3, we're going to put the identity matrix on the right hand side. Then these numbers have to match in order for it to be possible. So this has got to start with 3, and identity matrix is always a square matrix, so it has to end with 3 as well. So we take the 3 by 3 identity matrix with ones on the principal diagonal, zeros everywhere else, and we're going to multiply it. So, as always, we cut the one on the left into rows and this one into columns. And we'll move a little quicker in this one. So this is row 1, column 1. So we're taking row 1, timesing it by column 1. 3 times 1 is 3. 5 times 0 is 0. 4 times 0 is 0. 0 plus 0 plus 3 is 3. Okay, row 1, column 2, and it goes here. 3 times 0 is 0. 5 times 1 is 5. 4 times 0 is 0. 0 plus 5 plus 0 is 5. Row 1, column 3, and it goes here. 3 times 0 is 0. 5 times 0 is 0. 4 times 1 is 4. 0 plus 0 plus 4 is 4. And now we'll look at row 2, column 1. So take the numbers in row 2, times them by the numbers in column 1. 1 times 1 is 1, plus 0 times 0 is 0, plus 2 times 0 is 0, 1 plus 0 is 1. Row 2, column 2. 1 times 0 is 0, plus 0 times 1 is 0, plus 2 times 0 is 0, 0 plus 0 plus 0, 0. Now, row 2, column 3, we take the numbers in row 2 and times them by the numbers in column 3. 1 times 0 is 0, plus 0 times 0 is 0, plus 2 times 1 is 2, 0 plus 0 plus 2 is 2. And as you can see, the answer and the factor that wasn't the identity matrix, they match. The identity matrix is doing what it's supposed to do. Let's move on. Okay. All right, now let's talk about an inverse matrix. An inverse matrix is the matrix that you can multiply a given matrix by and get the identity matrix. Only square matrices have inverses, so not all matrices have inverses. If they're square, they might have an inverse, and not all square matrices have inverses. Okay? The case where it doesn't have an inverse, if the determinant of a square matrix is equal to 0, then it doesn't have an inverse, and you'll understand that in a second when you see the definition down here. Okay, so in general, then any matrix A times a to the negative 1, and this designation is for the inverse of A. So this is our way of our shorthand for inverse of a to the negative 1. And that should multiply to give you the identity matrix. Now, this could be a 2 by 2 or a 3 by 3 or a 4 by 4, depending on how big A is. Then you'll get whatever the identity matrix would be for that size. That's what you get here. All right. Well, in general, again, if A is this matrix A, B, C, D, and we'll put in numbers in a little bit, then the inverse of A, or a to the negative 1, is defined as this right here. So we need to get this, not that you're not writing all of this in your notes, but let's go ahead and make sure this gets in your notes. A to the negative 1 is defined by the fraction 1 over the determinant of A, so that's the determinant of this matrix, and that times this matrix D, negative B, negative C, A. Okay, so a little note down here, the determinant of A, how would you find the determinant of A? It's the arrow going down, or the diagonal going down, A times D, and it's always subtract, minus the diagonal going up, C times B. So that's going to be a number. It might be 1, it might be 5, negative 2. It's going to be some number that's going to complete this fraction. Okay, so an inverse of a matrix A is found by taking 1 over the determinant of A and then timesing it by this matrix here. Now, let's take a look at this matrix and compare it to this matrix A, where we had A, B, C, D. Okay, if you'll note, there's changes in these matrices here happen on the diagonals. Look at D and A and D here. And of course that change could simply be described as on this diagonal, those numbers changed places. And then if you look at this diagonal, C and B, we have negative C and negative B. Now they didn't move, but what happened is they changed signs. Now this is not to say that this number is always negative. It's just always going to be the opposite of what this one is. And negative C, or the opposite of C, will be the opposite of whatever this is. So if C is positive 2, then this would be negative 2. If this was a negative 3, then this is going to be the opposite of it, positive 3. So that's the meaning of the negative C. It's going to be the opposite of whatever it is over here. Okay, that's not new to Algebra 2. You guys have seen that with different formulas before. The vertex of a parabola or an absolute value, negative hk and negative h always lies, k tells the truth, if you'll remember that. Okay, back to example number 2 now. Okay, so we want to find the inverse of a given matrix B. So here's B, 3, 1, 4, 2. Okay, step 1 of finding the inverse. Now, I gave you the formula for inverse on the screen before this, and I hope you wrote it down. But step 1 is going to be find the determinant of B, of the matrix that you're trying to find the inverse of. I should go back and say that I noticed that it was square we know only square matrix have inverses. So I saw that this was a 2 by 2, so we proceed and then we find the determinant. Now, if you're wondering why well, we'll leave that off right now. Okay, so let's find the determinant here. So it's going to be 3 times 2, always minus 4 times 1. 3 times 2 is 6, 4 times 1 is 4, 6 minus 4 is 2. Okay, so now here is the formula from the other page. So we complete that fraction up front, so it's 1 over 2. And now what happens to these numbers in this matrix that we write here? So it's going to be that fraction times a matrix with certain changes done on the diagonals. And of course, I've got it written up here. These two changed places, didn't they? So the 3 was up here and the 2 was down here. They've traded places or changed places. And the 4 and the 1, well, these two changed signs. Okay? So it became -4 and -1. Well, the next thing we need to do is to take that fraction and multiply it through this matrix. And of course we know that we just give it to all 4 of them. So I've done that right here. So it's going to be 1/2 times 2 right here. 1/2 times -1. I wrote that here. 1/2 times -4. And then 1/2 times 3. Okay? And then 1/2 times 2. Well, the 2's would cancel. You'd get a 1. And 1/2 times -1 is -1/2. 1/2 times -4, -2. 1/2 times 3, I'll just write that as 3 over 2. This is the inverse of B. And if we were to take the time to multiply this matrix times this matrix here, and I'm not going to do it right now, but we would get the identity matrix. Okay? All right, so find the inverse of A. Okay? So I'm going to go ahead and give you a little time to do this one. Okay, well, you should have gotten this matrix right here, 1/2, -1/4, -1/4, 3/8. Okay, going through it real quick here, 1 over the value of the determinant. The determinant is going to be 3 times 4, or 12, minus 2 times 2, which is 4. So the fraction out front is 1/8. Multiplication is implied. And then we take and multiply 1/8 times 4, and we put it here. 1/8 times -2, we put it here. 1/8 times -2, we put it here. 1/8 times 3, we put it here. Making those fractions by putting them over 1. 4 and goes into itself once and into 8 2 times, so we have 1 over 2. 2 goes into itself once, 2 goes into 8 4 times, we have -1/4. The same thing for this, -1/4, and then 1 times 3 is 3, 8 times 1 is 1. Now, it shouldn't be any surprise to us that we wind up with a matrix that have fractions in them, because by definition the inverse is a fraction times some matrix, and so a lot of times we wind up with fractions. All right, need to properly practice more than one of these, so go ahead and start on this one down here, and we'll come back in a minute. Okay, back with you. And the answer, 1/2, 1/4, -2, -3/2. All right? Okay, let's move on. All right. I think I went 2 pages here. Let me back up. Okay. Solving a matrix equation with inverse or inverse matrices. Okay, going to look at this real quick. All right, so we're going to let A be defined as this 2 by 2 matrix, and let B be defined by this 2 by 2 matrix. And we want to solve the equation A times C equals B by finding C. Okay, so this is going to be a matrix equation. So what we do is for A, we put the matrix in, and for B, we put this matrix in here. Now, this is a multiplication problem, so if you think about dimensions and the answer, then C must be a 2 by 2 matrix, because then for the multiplication to be possible, the first number would have to be 2, right? And then if the answer is going to be a 2 by 2, then the numbers on the outside would have to be a 2. So clearly then C has got to be a 2 by 2 matrix for the dimensions to work out. So you need to think about that. All right, so step one is going to be to find the inverse of A. So this is how we're going to solve this thing, is by using inverses. Okay, so let's go over that. A to the negative 1, which is our designation for the inverse of A, is 1 over the value of its determinant. Well, let's see what the value of the determinant is. 4 times 1 is 4, minus negative 3 times negative 1 is positive 3. 4 minus 3 is 1. Now let me go ahead and suggest to you that 1 over 1 is equal to 1, and so the fraction is really not going to affect this answer at all. So that times, okay, on this diagonal, these numbers trade places. On this diagonal, these numbers change signs. So the 1 times the changed matrix on the diagonal, we made the diagonal changes, 1 times that is going to be itself. Okay? Step 2 is going to be to multiply both sides of our equation by the inverse of A. So up here we're going to put A to the negative 1 in front on the left side here, and we're going to put A to the negative 1 in front of this B. And if you think about it, a matrix times its inverse is going to give us the identity matrix. So we'll see how that works out in a second. All right, so next page here, I've gone ahead and put, this was A times C was equal to B. Okay, and of course what we've done is we've put the inverse of A on the left-hand side on both sides of this equation. We couldn't put it on the left-hand side over here and on the right-hand side over here. That multiplication may not work. Okay, so here's the inverse of A from the last page. Here's A, and this is what we want to find C. And over here, the inverse of A times B. Okay, now we're not going to always work this out, but I'm going to work this out this time just to go ahead and show you that what we're getting from this inverse formula actually performs what it has the performance of what an inverse should do. So we're going to take row 1 and times it by column 1. 1 times 4 is 4, plus 1 times negative 3 is negative 3. 4 and negative 3 is 1. Row 1 times column 2. 1 times negative 1 is negative 1, plus 1 times 1 is 1. Negative 1 and positive 1 add together to be 0. Row 2 times column 1. 3 times 4 is 12, plus 4 times negative 3 is negative 12. Positive 12 and negative 12 add up to be 0. And then row 2 times column 2, 3 times negative 1 is negative 3, plus 4 times 1 is 4. Negative 3 and 4 is positive 1, and thus we get the identity matrix. Now, we already said that this is going to be a 2 by 2 matrix, right? We figured that out to start with. So this 2 by 2 times this 2 by 2, what happens when you multiply something by the identity matrix? It doesn't change. You get C. Okay, so it's not going to change. So basically, when we take the inverse and times it by this matrix over here, this side is going to cancel, and we don't always do this step here where we multiplied A times negative A. A times A to the negative 1. We won't always do that step. I did it on this problem just to show you that it does actually work. Okay, so over here we break this one up into rows and this one up into columns, and we proceed with our matrix multiplication. Row 1 times column 1. 1 times 8 is 8, plus 1 times negative 6 is negative 6. 8 and negative 6 is 2. Row 1 times column 2. 1 times negative 5 is negative 5. Plus 1 times 3 is 3. Negative 5 and 3 is negative 2. Doesn't look like a negative 2. Negative 2. Row 2 times column 1. 3 times 8 is 24, plus 4 times negative 6 is negative 24. Positive 24, negative 24 is 0. Row 2 times column 2. 3 times negative 5 is negative 15, plus 4 times 3 is 12. Negative 15 and 12 is negative 3. So C equals 2, negative 2, 0, negative 3. Well, I'd like to go ahead and check this. Well, we won't always do this either, but remember, our A matrix was from up here, 4, negative 3, negative 1, 1. Our C matrix that we just found by solving is going to be 2, negative 2, 0, negative 3. And that's supposed to be equal to the B matrix, and I want to see if it actually works. So we're going to go ahead and do this multiplication. B is 8, negative 5, negative 6, and 3. Well, let's see if it's true. This one's broken up into rows. This one's broken up into columns. Row 1 times column 1, or 8 and 0, is 8. That checks. This is our B matrix. Row 1 times column 2, we have negative 8 and a positive 3. That's going to be negative 5, and that's what we have here. Row 2 times column 1, negative 6 and 0 is negative 6. And row 2 times column 2 to give us this answer, we have negative 2 times negative 1, positive 6, and a negative 3 adds up to be positive 3. And sure enough, C is the 2 by 2 matrix that you could multiply A by and get C. So that was our solution, and we plugged it in and we saw that it did what it was supposed to do. Okay, let's take a look at one of these. I'll get you to try this. You might want to look back on your notes on the last problem and look at the procedure that we did. Okay, doing this in parts, then if we called this first matrix A times C equals B, like we did in the last problem, then we would, first step would be to find the inverse of A, and we did that right here, so you can check your work. Alright, back with you. Then the second step after we found the inverse of A would be to put it in the front on, excuse me, I say front, I mean the left-hand side on both sides of this, so we put it in front of A, and here we have A to the negative 1 times A times C is equal to A to the negative 1 times B. Now, I went ahead and did this multiplication out again. 21 and negative 20 was 1, negative 28 and positive 28, 0, negative 15 and, excuse me, positive 15 and negative 15 add together to be 0. Then negative 20 and positive 21 gives us 1. But this is always going to work out to the identity matrix, and that times anything is itself. So we're not going to always do this. Really, the answer comes from multiplying these over here. And of course, we broke this one up into rows and this one up into columns. And then we got negative 29, negative 48, negative 21, and negative 34. That's our answer. Okay. And let's try one more of these. Okay, coming back to you on this problem, we'll designate this first one as being A and this last one as being B, as we did in the last problem. So first step is to find the inverse of A. So it's 1 over the value of the determinant, 1 times 7, 1 times negative 7, minus a negative 8, which is going to be plus 8, negative 7 plus 8, times the matrix. Well, negative 7 plus 8 is 1. 1 over 1, 1 times all of this is itself. So this is the inverse of A, and we put it in front. So this is A inverse, and there's A, and then times C equals A inverse times B. Okay, now we're not going to go through this now. We're just going to say any matrix times its inverse gives us the identity matrix, and that times something is itself. So basically this cancels and we get C. Over here is where the work comes in. So rows and columns, and we get negative 51, 4, negative 29, and 1. All right, so just for a second, let's go ahead and see if it actually does what it's supposed to do, and let's plug this back into the equation. So the A matrix is 1, negative 2, 4, and negative 7. We just found C, so we'll write it next to here, negative 51 and 4, negative 29 and 1. And let's see what we get when we multiply these two together. Hopefully it turns out to be B. So when we get we'll compare our answer to B, because A times C is supposed to equal B. Let's see if it does. Broken up into rows, broken up into columns. 1 times negative 51 is negative 51. Negative 2 times negative 29 is positive 58. A positive 58 and a negative 51 is 7. And that checks. row 1 times column 2. 1 times 4 is 4. Negative 2 times 1 is negative 2. 4 and negative 2 is 2. That checks. Row 2 times column 1, make that look like a 4 there. It's going to be 4 times negative 51. That's going to be negative 204. And negative 7 times negative 29. Well, 29 times 7 is 3 carry a 6. 14 and 6 is 203. And negative times negative positive. Negative 204 and positive 203 is 1. Let's see, no, it's going to be a negative 1 because the negative's bigger here. Negative 204 plus 203 is negative 1. And row 2 times column 2, 4 times 4 is 16, 16 and negative 7, 9. And as you can see, that is the matrix that you can multiply A by and get this B matrix. Okay? Well, that concludes this video. Thank you for watching. I'll be making an assignment for the class.